Okay, I'm back. Right, so we got our total CFA to work, CFA with the total data set. So now, of course, we want to know how well do these dimensions work in the different data sets. And I'm going to show you a couple of different ways. In this session right now, I'm going to show you one particular way, and then in the next couple of sessions, we can look at a couple of other options. And the simplest way, or one of the ways that I think is actually quite useful to do this, uses the same kind of commands, but will introduce an additional little command line that specifies the groupings in our data set. Right, so let's just start off running the CFA with the, or by group, let's say by this. And if you remember, what kind of level of invariance was that if we test whether the instrument actually shows comparable factor loadings across different samples? What kind of equivalence was that? Do you guys remember? Dung, 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 dung. And the answer is that is probably closest to structural equivalence. And in invariance terms, it's often called configural invariance. So what we're going to look at right now is essentially we're going to create a new model, model 1, and let's call it maybe configural. And we are going to set up again a CFA model. So we are going to run the same model. We have the same data. Data example. Let's go with actually standardized like variable equals true. And then what we want to do now is we want to basically say what the group is. And the group in our case is captured by the country variable here, right? So if we run this, we now have to again specify what we want to get shown. So we want to have fit measures. Oops. We want to have the standardized solutions. And actually we could ask for R squares as well, but for simplicity's sake, let's just focus on the simple output, or somewhat simpler output. Oops, what did I just do? Right, so we now run it, Control Enter. What happened there? What could be the mistake? I think it is this one. Let me check. Yes, okay, it's fit dot measures. Okay, we have a lot of output now, because what will happen now is we again have our overall kind of information on the estimator, the optimization method, and then it tells us the number of observations per group. Right, so we can see our effective sample sizes, and I will quickly skip forward here for a second, and then it will give us the output, all the parameters separately by group. So here we have an NZ, then we have Brazil, then we have Canada, and we have the Philippines. And it will also now give us a chi-square separately for each country, not with the specific chi-square p-value, but it will give us the breakdown of the overall chi-square value. So if we would break this down, what portion of this chi-square value is due to what sample. So again, it's quite significant, and we can see that the smallest contribution is actually from Canada, and the largest contribution is from New Zealand. If you have a look back here, actually New Zealand has the largest sample size. So the fact that New Zealand doesn't proportionally contribute more than the others is actually a good sign. Most likely the data will fit quite nicely in New Zealand. So, you know, bits and pieces you can start, because we know that the chi-square value is dependent on sample size. New Zealand sample size is much larger, and the chi-square is not that much larger, so that already, you know, like, it's kind of little bits and pieces, you know, like that you can pick up. The important thing here is now the comparative fit index and the Takarlui index. It dropped a little bit, so it's now just below the 0.95, and the TLI value is 0.93, so it dropped a little bit, and I will get back to that a little bit later. Our RMSEA has increased, so if you remember, it was just above, or was just around the 0.8 mark, and now it's 0.89. And this SRMR, I can't remember off the top of my head just now, but it's still pretty good. And then we can see the latent variable factor loading, the factor loadings of each item on the latent variables. And as you can see, all of the items load significantly in New Zealand, so that's pretty good. So and pretty even factor loadings, pretty like evenly distributed factor loadings across all items. That's encouraging. Correlation is pretty high between the latent factors. The intercepts are now estimated. So this is essentially the mean of each of the items, and the intercepts for the latent variables are 0, because we need them to be 0 in order to estimate the item intercepts. The variances again for the specific items, and then we get to the next data set, which in this case is Brazil. Here we see that we can see again that all of the items load significantly. Interestingly, the first item also shows, if you remember, somewhat smaller loading. The first two items show somewhat smaller loadings. The last one also is a little bit smaller overall. And for voice, the same thing. All of them are significant, pretty even loading on average. The correlations are pretty high, similar size as before. We have the intercepts here, we have the variances. I don't want to get through all this material now in great detail. I want to focus on the bigger picture issues. We have the Canadian sample. Again, all of the items load significantly. The standardized loadings are pretty comparable. The first two items for helping again are a bit lower. For voice also, all of them are significant, pretty even loading patterns overall. Covariances about same, covariances of the latent variables about the same strength, and then the intercepts and the variances. And lastly, the Philippines here. Also, all items load significantly, and yeah, again, quite even loadings overall. And the correlations between helping and voice seem to be a little bit higher. Cool, so that's all good, but the interesting question right now is, so if we think about it in terms of like structural equivalence, all of the items load on the latent factors, and we can actually conclude, yeah, it seems like we have structural equivalence for these particular items in these 4 different samples. But then obviously we can't make any conclusions about the strength of the factor loadings. You know, like, are the factor loadings actually comparable? For that, we need to look at what? Do you guys remember? Running the CFA by group. What is the next level of equivalence? Exactly, metric equivalence. Yeah, and that's also metric equivalence, metric invariance. So constraining the, what do we constrain right now? Exactly, factor loadings to be equal. So how do we do this? We're going to use the same kind of approach right now. We're going to again use fit model 1, and now we call it metric. We use the CFA command, model 1. We use the same data, so data dot example, standardized latent variable. We want to do this, and now I just bring it to the next line here. Group equals country. What we need to show now, or what we need to define now for R, is basically the parameters that we want to constrain to be equal. So we go group dot equal, and we have to specify what we want to constrain. We want to constrain, oops, thank you for notifying me, there's a missing comma here. We need to tell R that we want to have the loadings to be constrained to be equal. So as you can see, it's very logical. We go step by step, we specify what the grouping is in our data, and then we say what should be equal or kept constrained to be equal across groups. And right now we want to keep the factor loadings to be constrained to equality across samples. So we run this, it ran without problems, and we again want to get the output summary fit model, oops, one, fit metric, then we have fit measures equals true, and standardized equals true. Fantastic. Let's see what happens. The output will look very similar again. We will start off 94 iterations first of all. The estimators, the optimization method, and then we have a couple of new lines. We have the number of free parameters. We constrain some, so we gain some free parameters, and we have a number of equality constraints now in our data set, because we have all the different loadings that are constrained to be equal across groups. We have our number of observations, and now we have our chi-square tests here again, and we have again the chi-square test value broken down into the components that are due to the dataset from New Zealand, Brazil, Canada, and the Philippines. If we look at our CFI, it's about similar, 0.94. I think it was maybe a split marginal, like minute dust particle higher. Tucker-Lewis index is also just below, like the commonly accepted threshold. The RMSEA is just a bit above where we want it to be, and SRMR is okay-ish. Right. So now, pay attention to the following parts of the output now. So we have our Group 1 New Zealand. We have our factor loadings. And now you have a new little column here which goes like P1, parameter 1, parameter 2, parameter 3, etc. And if you will notice something now, this value here, 0.91, is the factor loading for item 1 on the first latent variable in New Zealand. If I scroll down now to Brazil, we have help, item number 1, parameter 1, it's exactly the same. Because right now we constrained all our parameters all the factor loading parameters to be the same. So we will not see any differences anywhere along these columns at the moment, right? So now you may think, so how do we actually know whether what we did was good or not? You know, like, can we actually conclude that we have metric equivalence based on these results so far? One option is to look at just the fit indices the way we have done before. So ignoring that we have different kind of models, and based on that we would argue that probably we are still in kind of marginal territory. So we have our CFI is just below, you know, like traditionally accepted cutoffs. So you might be able to get away with it. But people also started looking at the comparative model fit, because now we have so-called nested models, because we have a relatively unrestricted, or we have an unrestricted model, which is our configural model, and then we have a more restricted model, which is the metric equivalence model. So we can actually look whether the fit got comparatively worse compared to the less restricted model. You see? So we can actually compare whether our data, you know, fits significantly worse. The way to do this is we could, for example, run an ANOVA on the chi-square. So we compare the chi-square value for one model compared to the chi-square value of the other model. Magically, the way to do this is fit model one configural. Oops, model one configural, right? So we basically call a little ANOVA command here, which now compares the first model against the second model, right? And if we run this, what it will give us is, it will give us the degrees of freedom. So a chi-square difference test, degrees of freedom for the first model, 212, degrees of freedom for the second model, which is more constrained. That's why we have more degrees of freedom. It will give us also the AIC, BIC values. So some people, especially in the Bayesian world, love AIC and BIC values. I think we shouldn't worry too much about them right now. If we want, we can discuss them later. And then this chi-square, the chi-square values for the two different models. So for configural, the configural model, it's 1598.8. For the metric model, it's actually a little bit larger. The difference between these two models is 82. And because now we have all these additional free parameters, so the degrees of freedom, the difference in degrees of freedom is 30. And if we look this up in a chi-square table, so this value against 30 degrees of freedom is actually highly significant. And now if we would follow kind of exact fit criteria, then we would say, oh my god, it fits significantly worse. So no, we don't have metric equivalence. But we also know that chi-square values are very, very sensitive to sample size. We have a huge sample. We have huge samples from the different countries. So people have argued that's actually not the best test. And so another option would be to actually compare the configural test values. So we could, for example, because we would need to go through our output again and try and get all these fit indices out. A simple way of potentially getting it into one simple line, we could go, for example, fit measures, what model we want to see, fit model configural, and then we want to get all the relevant fit indices that we might be interested in, CFI, TLI, could ARM, SE, ARM, SEA. For the heck of it, might just go for all the ones that we've been talking about so far, and we could also go for the chi-square again, oh sorry, it's just like that, and our degrees of freedom. And if I now run this, we get our CFI, TLI, RMSEA, and so on and so on values here. And we of course want to have the same information from the other fit measures, fit model 1 metric, and we go see. It's good practice to like to type everything again. If you're busy, you could also just copy the line above, but you know, it's a bit of mindfulness practice, and it's like meditation, isn't it? Cool. Do we run it? Is this looking okay? Yes, it is. Whoa! Here we go. So we now can see the values pretty neatly. So we have the CFI values for the configural or structural model, and we have the CFI values for the metric model, and we can look at the difference between the two values. And here what is interesting, people have argued if the fit is smaller or smaller than 0.01, then we still have equally good fitting models. So if I would go, you know, like this fit value here and this fit value here, you know, just for the sake of it, oops, what was I doing here? 0.946. I mean, those of you who have working brains, they will have worked out that the difference is 0.002. So it's actually a tiny difference, and we can safely conclude that based on the difference in the CFI value, that probably the fit is not substantially worse. We can do the same kind of comparisons for the TLI and also for the RMSEA, and the cutoffs are similar. So whenever the difference in fit is smaller than 0.01, we can safely assume that the models are comparable. So based on the chi-square, we would argue no, our model fits significantly worse. Based on these comparative or incremental fit indices and comparing their difference value, we would actually argue that we have equally well-fitting models. So hooray for those 4 data sets with these 2 dimensions from this particular survey. We would argue, okay, we have structural equivalence. Hooray! So that's good news. But we also would want to see whether our intercepts are actually equal or not. So now we have up here running the CFA by group, and we tested metric equivalence or invariance, but we also want to now test what happens if we constrain the intercepts to be the same. So running the CFA by group, and what is this level of invariance or equivalence called? Exactly, scalar or full score equivalence, invariance, and constraining intercepts to be equal, right? So that's what we want to do right now. We will use the same kind of approach again, same kind of idea. So we go fit model 1, and we call it, let's say, scalar. Go CFA, what model we want to run, so model 1. What data do we want to use? We want to use data example. We want to use standardized latent variables equals true. Group equals country, comma, and then group equal. What do we want to set to equal. We want to set to equal right now the loadings, and importantly we also want to set now the intercepts to be equal, right? So same as before, just now we want to simultaneously constrain both loadings and intercepts to be the same. We run our model. We want to get our output summary fit model 1 scalar, etc., etc. Yeah, let's go through it. That's fine. Fit measures equals true. Oops, equals true, and standardized equals true. Right. So if we run this now, first thing again, took a few more iterations. We have many more equality constraints because now we constrain the intercepts as well as the factor loadings. We still have the same number of observations. We have a slightly larger chi-square as could be expected because now we have a much more restricted model. And we have our CFI and our Tucker-Lewis. Whoops, it dropped a little bit. Will be interesting to see. Our RMSEA went up a little bit and the SRMR went up as well. The interesting thing right now is if we now go to our parameter estimates, we have again all the factor loadings here that are constrained to be equal. So this factor loading here, 0.908 in Brazil, is exactly the same as up here. And now we have additional constraints on our intercepts. So for the first item here, it is parameter constraint 28. The estimate is 5.21, and if we scroll down, it's exactly the same intercept here for Brazil now. And so the question now would be, how good or bad is that fit? So we could again run an ANOVA and compare fit model. Now we would pick the metric model as comparison, and we go fit model scalar. And what you can see now, the degrees of freedom for the metric model versus the scalar model, the difference here is again 30. And what you can see here is the chi-square is actually quite large, 301.69. 30 degrees of freedom. This is highly significant. So according to the chi-square difference test, we would argue that no, our loadings, our intercepts are substantially different between, or significantly different between the groups. But if we again go with the comparative fit indices, so we would go fit measures, that was the command, yeah. Fit measures, fit model 1 metric, and we want to specify which ones we want. So CFI, let's just go TLI, RMSEA. Let's go with these ones for the time being. And then fit measures, fit model 1 scalar, and C. Hope you can see this here. C, CFI, TLI, and RMSEI. So now if we highlight both of these at the same time and run it, what we now see is the difference, or we can compute the difference between the CFI for the metric model versus the scalar model. What you can see here is that the difference between this and that is actually 0.01. The difference between the TLI for the metric and the TLI for the scalar is actually 0.003. And here we have a difference of 0.002. So it's kind of tough right now. I I personally would say that we are right there on the threshold. There might be some intercepts that are not quite the same across the different samples, but overall the pattern is pretty good. So we definitely have metric equivalence for our instrument, but whether we can compare the means directly, we may have some intercepts that are a little bit divergent across groups, and that's something that we can maybe discuss in due course. But yeah, so this is essentially, these are the important steps for testing whether you have configural, metric, or scalar / full score equivalence. So I hope that seems to be not too difficult, and if you have questions, let me know. It would be great if you just use this code and run it with on your own computer and see if you can reproduce these results. Okay? Awesome.